Great. Okay, can you hear me? Yeah, great. Just one sec. Okay, so today I want to introduce the last ingredient and then put everything together. So let's start by the last ingredient. So modular symbols. Okay, so we have the modular curve, x1 p to the r, thinking of it over C for a moment. Right, of course, it's the union of the modular curve y1 p to the r and the cusps. I'll call that C1 p to the r. And so C1 p to the r, of course, is it's the cusps, which is P1 of Q, or Q union infinity, modulo the congruent subgroup gamma 1 p to the r. So what's a modular symbol? If I have two elements of Q union infinity, say alpha and beta, modular symbol is the class in the homology of x1 p to the r relative to the cusps of the class of the geodesic from alpha to beta. So let me draw that. So first I'll write, it's in this group. Okay, and it's the class of the geodesic, so I mean really any path here, alpha, beta. So that would be alpha, beta, or if I had a gamma here and I could take the straight line to infinity, that would be gamma infinity. Okay, so these things generate this relative homology group, and in the 70s, Monin proved, gave a nice presentation of this relative homology group on some of these modular symbols. Let me tell you which ones. Okay, so this H1, just write the same group here again, is generated by symbols called Monin symbols, UV sub R, which are equal to a matrix, gamma, times the class of the path from 0 to infinity, thinking of acting on 0 and infinity separately, which the matrix will be A, B, C, D, so you can work out that that's B over D, A over C. So, so here, gamma is A, B, C, D in SL2Z, and UV, okay, so I didn't say where UV are. Okay, so UV are numbers mod P to the R. UV is CD mod P to the R Z squared. So in particular, put that here, where U and V are in Z mod P to the RZ, their GCD in that ring is 1. In other words, they're not both divisible by P. So that gives you generators. There are also relations. So with relations, and they're very simple. UVR is minus U minus V, and that's the same as minus VU, and that's the same as U plus V plus U plus V. And those are all the relations. You do this for all U and V. So that gives you a nice finite presentation of this abelian group. Okay, so now I need to, these aren't quite the symbols I want, so I'm going to make two modifications. The first is I want to project to the plus part. So I'll work with ZP coefficients here, but in what I'm doing, you could work with Z1 over 2 coefficients, despite the level being P. Okay, so here in the entire construction of this map I'm going to make. Okay, so UVR plus will be 1/2. So this is what happens when you apply complex conjugation. You actually get minus UV. So I'll just sum the thing in its complex conjugate. So this will lie in H1 x1 p to the r, c1 p to the r, zp, because p is odd, so 2 is invertible, and plus fixed part under complex conjugation. And then I want to modify that by applying an Aitken-Lehner involution. So what does that amount to? So Wn corresponds to the matrix -1 n 0 0. And so the effect of that is that you get the class of the modular symbol d over b p to the r goes to c over a p to the r, and then projected to the plus part. So it's a sum of 2 symbols, really. Okay, so that's the symbol I actually want for all u and v. And so these also present a group, and let me tell you which group they present. C1, they generate. C1 not p to the r will be some subset of the cusps. So there's 2 ways to think of this. You could think of this as, I call this the non-zero cusps. So, or actually, Fukai and Kato called it the non-zero cusps. So you can think of this as the cusps that don't map to 0 on the modular curve x naught of p to the r. Explicitly in this case, this is the cusps that are represented by fractions a over b, relatively prime, reduced fractions, where p does not divide b. Okay, so I could look at this group, SR naught, which will be the homology relative to the non-zero cusps, these non-zero cusps, and plus part. That'll be the definition. SR circ, yeah. So, okay, this thing is actually Hecke stable. So the Hecke operators act on these groups, and this thing is stabilized by the Hecke operators. Well, but it also has a nice presentation, which is a corollary of Monen's theorem, and that is that SR naught is generated by the UV with the same condition, but now we add the condition that UV are not 0, star, with UV not 0. And with the same relations essentially, but now we've projected to the plus part, so they actually simplify a little bit. So UV R star is now the same as its complex conjugate, and that's the same as now just minus VU. And if I take a U plus V that's not 0, at least, then I have that it's equal to this. Yeah. Okay, so that's a simple presentation of this group, and so that's why actually we take this group, because it has this nice presentation. And inside this SR naught will be actually the homology of the closed modular curve, plus part. But it's not as easy to say what it generates it. Okay, so now let's recall that we had in the last talk, we had a cup product pairing, which I could restrict to cyclotomic P units. So recall, right? We had this pairing, cup product pairing, on cyclotomic P units. Let's call that in FR, remember FR was just Q mu, oh, that's a weird F. FR is Q mu P to the R. Okay, so the cyclotomic P units, if I denote them by CR, CR cross CR goes to H2 GR ZP2 actually lands in the plus part on cyclotomic P units. So GR here was Galois group of maximal P ramified extension of FR. And I should give this some symbols, right? So that's the pairing. Right, the Arth pairing. So it's just given by cup product. And we had conjectured it was surjective, McCallum and I. Okay, so surjective when you consider it, or span of the image is the whole thing. Okay, so here's a theorem. Simple one, but it's very interesting. Independently to by Buziok and myself, there exists a map pi r from SR not to Y. Oh, what's YR? Let's call this thing YR so I don't have to write it again. Okay. Okay. There exists a map pi r from SR naught to YR, and pi r of the Monin symbol UVR star is just the cup product of 1 minus zeta p to the r to the uth power, 1 minus the p to the rth root of unity to the uth power, and 1 minus a p to the rth root of unity to the vth power. A homomorphism. In fact, of what? In fact, it's a homomorphism not just of ZP modules, it's a homomorphism respecting the action of delta on both sides. Delta, remember, was this group. So what was the action of delta here? The action here is by the inverse of diamond operators. So if I have J and delta, then I can act on left by delta J inverse, and that takes the symbol to JU, JV, you can check, and act on right by sigma J, where the p cyclotomic character applied to sigma J is J. So chi p was the p cyclotomic character in previous talks. So okay, so and that will just raise the u to the root of unity to the jth power, both sides. Okay, so what's the idea of the proof of this? For instance, for the last Monin relation, the complicated one. Well, just remember that we had, if I set zeta to be zeta, the p to the primitive p to the rth root of unity, remember that I had this sum of cyclotomic p units being 1, which told us that if I pair, so the root of unity turns out pairs trivially with everything. So this tells us that because we know x and 1 minus x pair trivially, that this cup product is 0, right? And now this is bilinear, right? And antisymmetric. So now if you just multiply this out, you get 4 terms, one of which disappears, and the 3 things you're left with look exactly like this relation, UVR equals U plus V, U plus VV, right? So then this gives us the, corresponds to the last Monin relation. right? You just need to show this is a well-defined map, you need to show it's, right, for any thing in the presentation, right, you need to show that goes to 0. Okay, so that's the idea. Relation. Okay, great. We actually showed a little more than that, but there's a stronger result. And that's the theorem of Fukaya-Kato, which I conjectured. So the theorem of Fukaya and Kato first theorem is that this map factors through the quotient of the left-hand side by the Eisenstein ideal. So I here, I can define it without reference to K. In the last talk I was using a K because I was choosing a particular eigenspace for the action of delta. Here I could just use the diamond operator instead of applying a character. So I is generated by TL minus 1 minus L diamond operator L for L prime not equal to P, and UP minus 1 for L equal P. Okay. So it's like Elf Hecke operator minus, well, something giving coefficients of several different Eisenstein series, the Elf coefficient. Okay, so some remarks on this. The first is that actually if I look at ordinary parts, and once I go mod Eisenstein, everything is ordinary because UP is 1. And, you know, ordinary means like UP is a unit. So if I'm 1 is a unit. Okay. And SR ord actually equals SR circ ord. So I can forget about the circs. So this implies that SR mod I SR is SR ord mod I, SR circ mod I SR circ. The second is that, so this gives us a map, which I'll call by a different letter. This capital pi r factors through this lowercase pi r, which is SR mod I SR by their theorem to YR. So now we have a map like that. The second is that these things are compatible in the tower. Okay? So in other words, what you can check that if I look at R plus first symbol, PU and V, that maps under the standard map coming from the identity on the upper half plane of modular curves from x1p to the r down to x1p to the r plus 1 down to x1p to the r. This maps to u v r star. And also 1 minus zeta p to the r to the u and 1 minus zeta p to the r plus 1 to the v, r plus first symbol maps to 1 minus zeta p to the r to the u, 1 minus zeta p to the r to the v, rth symbol, under co-restriction or norm. And actually by Nakayama's lemma, since these things generate below, these things will generate everything above. So even though there are more symbols, these things actually generate the homology above. So, so this tells us that we're compatible in these maps are compatible. So in other words, I can define, maybe I'll just write it here. So this means that there's a map var pi, which is the inverse limit of the pi r's, and it maps, so I will need the next slide, S mod is to y, where these things are the inverse limits. So in other words, here, S is the inverse limit of the, we could take ordinary parts or not, but I guess since I don't need it, I won't. No cusps, sorry. And y is the inverse limit of these H2 groups of the GRZP2 plus. But remember that that was what we called Iwasawa cohomology. And remember that this group we showed, we can pull out the twist in Iwasawa cohomology, so this becomes x infinity 1 plus. The H2 with 1 ZP1 coefficients was x infinity, and the 1 twist switches plus and minus, so this is the same as x infinity 1 minus 1. So the eigenspaces of this are giving the odd eigenspaces of the inverse limit of class groups. And that's the thing that appeared in the main conjecture proof we did. Okay, so we have this map of our pi. Now I need to return. Yeah, so I'll just stop there because I need to return briefly to the main conjecture proof we did. Oh no, first. Yeah, no, I won't stop. I want to tell you something about how is this theorem proven, right? Okay, it's because it's interesting. Okay, so the idea is this. There's Ziegel units, so you've seen them, right? There exist Ziegel units. Those on Y1 of n were the ones that were in Sarah and David's lecture series denoted, well, with a C. I'm going to ignore the C. G0 something over p to the r. So I'll just denote them. We don't need the 0. I only I'm working with Ziegel units on Y1 of n. So Ziegel units GU in, don't need the over n. Y1 p to the r. This is over Z1 over p. Sorry for the, okay, that, right. So there's Ziegel units on this modular curve. Really, they're in this tensor Q because I didn't put the C here. So they have some denominators in general. And here U is an element of Z mod P to the R Z minus, not including 0. So think of this as U over P to the R. Okay. And then what the Kato's Euler system is, well, is actually not quite these cup products of Ziegel units, but it comes from cup products of Ziegel units. It's just basically what it is. It's not quite these cup products. But anyway, these cup products are called Balance and Kato elements. And so this thing lies in H2 tau cohomology, Y1 P to the R, Z1 over P, ZP2. Balance and Kato element. Okay, so what are the steps? One is they show that there's a Hecke equivariant map from S to this group. So let's call this H2 tau. Okay? So they show there exists a Hecke equivariant map, Z from SR naught to H2. I guess there should be an R on the H2 tau somewhere. But they show there's a map like that that sends this symbol to this cup product. Okay? So it seems even better than the map var pi. And the second thing is that there's a specialization at the cusp at infinity map. So you can think of infinity as being, in the model I'm taking, rational over the maximal totally real subfield of q mu p to the r, in fact, over this ring. So this gives us a a cusp on x1 p to the r. And there's some sort of specialization at infinity map, which is almost pulled back by this thing, but the cusp doesn't really lie on y1 p to the r. But the specialization at infinity map, I'll also call infinity, and this maps the H2 etal that I had on the last thing to H2 of this ring. Well, okay, so I haven't talked about etal versus Galois cohomology, but actually in this sort of setting, it's pretty much the same thing. So this is actually YR. I even have the plus here, right? So this is a specialization at infinity. And I guess the third thing is, what does it do to cup products of Siegel units, right? So remember that Q expansion, actually in this case it's a little bit simpler than what appeared in Sarah's talk, which is it's Q to the 1/12, n equals 0 to infinity, 1 minus Q to the n, zeta p to the r to the u, times a term I don't really need, but it's can't leave it out, n equal 1 to infinity, 1 minus Q to the n, zeta p to the r to the minus u. Okay, what happens when I specialize this? You can do this on H1 as well with ZP1 coefficients. So I could specialize this at infinity. What do I get? I should get some sort of unit, p unit. Well, what the specialization at infinity map does is it sort of forgets about the power of Q, and then it takes Q to 0. So if we plug in 0 into the rest, there's only one term that survives, right? And that is 1 minus zeta p to the r to the u. Okay, so under this specialization map, GU goes to this nice cyclotomic unit. So the specialization map is compatible with cup products. So in fact, GU cup GV therefore goes to 1 minus zeta p to the r to the u, cup 1 minus zeta p to the r to the v. So in other words, var pi, or pi, is infinity composed with z. And so then the fourth fact is that infinity factors z was Hecke equivariant through quotient by the Eisenstein ideal. In fact, this is not quite true, but it's true for all Hecke operators but up minus 1, and then you just have to do something a little special for up. So it factors through the quotient by the Eisenstein ideal, so therefore you're done, right? Because this is Hecke equivariant, this is Hecke equivariant, and factors through the quotient by I, so you're done. Very nice. Okay, so great. So now let me, I want to map, this is one map, var pi, okay? I want another map in the opposite direction. And that map is going to come from the proof of the main conjecture, which is why I went through it in such detail, other than it's good to know. And so let's just recall that we used this thing T, which was the inverse limit of etal cohomology groups. This is now over Q bar, ZP1, ORD in the corner. All right, that was the thing we used in proving the main conjecture. It fit in an exact sequence of local at P modules. Oh, yeah, quo doesn't come in the T sub, T quo, where this thing is as on inertia was, so this is as over for GQP, okay? On inertia, this thing was H as a Galois module, and then it had some twisted, as a Hecke module, and then it had some twisted Galois action, and this thing was just the lambdatic cusp forms, right? So this is the lambdatic Hecke algebra, cuspidal Hecke algebra, and this is lambda-adic cusp forms. This was as GQP, or as modules on inertia, just trivial action. Okay, so remember that we thought of our, this was rank 2 over the quotient field, if we tensor with the quotient field of is rank 2 over the Hecke algebra. It comes free of rank 2 if we tensor with the quotient field of lambda or of the whole Hecke algebra, total quotient ring. So we can think of it as giving a two-dimensional Galois representation, which is somehow giving you the Galois representations attached to all sort of cuspidal eigenforms at once. And so we thought of it as an A, B, C, D, where C was a map from Galois to right, Hom, oh yeah, I left myself no space. T sub to T quo. And from this we constructed some cocycle psi C, which was this times the inverse of the determinant, and psi C mapped, the key thing was that the C, right, we were upper triangular on inertia, so C was trivial on inertia, so it factored through the maximal abelian quotient when we restricted to Q mu P infinity, and this gave us a map like this, and this was surjective. And then we said that the characteristic ideal of this was divisible by the p-adic L function, so therefore the characteristic ideal of this that was a map of lambda modules. So I want to say something about this C. So this T sub is isomorphic to H, right? So as a Hecke module, this homomorphism group is just isomorphic to T quo. So Hom H T sub T quo is isomorphic to T quo as H modules. And so we can identify C with its image in here. And what did Ota really do? He replaced the lattice T. So I said you have a choice of lattice, right? And depending on your lattice, the Galois representation could look different. What's the smallest lattice, Galois stable lattice, containing T sub? Well, it's if we think of C as inside T quo, it's really just T sub plus C. And that's the lattice he uses, not really T itself. And this is how Wiles does the proof. And I should say, yeah, the proof I was giving was due to Ota, but it's very similar to the proof of Wiles, and Wiles would use this lattice, which is the lattice spanned by T sub as a Galois module. So the question is, can you use T itself, right? And actually, this is a recent theorem of Ota's, and not yet published. So thinking of T as in T quo, C equals T quo. So in other words, this T is actually the lattice you use in proving the main conjecture. You don't need to choose any other one. It's natural, and it's sort of the smallest in a certain sense. So, okay. So that's great. The second thing I want to say is, so now that this C is T quo, so fact, when we reduce mod I, a lot of things become canonical. I should just say things become canonical. But the point is that these isomorphisms here between T sub and the H and T quo and the lambda-adic cusp forms S are not canonical, but they become, in a sense, canonical when you tensor with the Witt vectors of the maximal and ramified extension. Well, when I reduce mod I, the point is that somehow on T quo, UP acts as Frobenius, and now I'm reducing mod UP minus 1's in my Eisenstein ideal, so Frobenius starts acting as 1, and somehow this means that actually these isomorphisms become canonical, at least the T quo one. So things become canonical. So for instance, S mod IS, which was this is my inverse limit of plus parts of modular forms. Well, this is really, just by Poincare duality, T plus mod IT plus. You could map this thing to, so that's fixed part under complex conjugation. You could map it to T quo mod I T quo. That turns out to be an isomorphism. And this thing is isomorphic to S mod IS. And all of these isomorphisms, I mean, I had to fix a decomposition group here, so canonical in quotes, but are canonical. And so actually, lambdatic cusp forms mod I is the same as these lambdatic modular symbols, cuspidal modular symbols mod I. And that's the same as T quo mod I. So it's also C mod IC because C is T quo. And the second thing is that T sub mod IT sub is actually also canonically that takes a little more work, but as also canonically isomorphic to H mod I iota 1, which remember was lambda mod my p-adic L function. Actually, I'll put lambda tilde plus here, iota 1. So this, I'm going to think of this C as all the different CKs at once. You should take C0, and so you can think of this instead of just being in lambda, it's in lambda tilde plus, where the kth one sits in the 2 minus kth eigenspace. Yeah, I think. Yeah, that's right. Yeah, so this becomes canonical. Somehow there's a generator which is somehow dual to the path from 0 to infinity under some Poincare duality.
Romyar,
yeah.
Check something in your notation.
Yeah.
The plus here is the complex conjugation eigenspace. It's not the subspace for the filtration of P.
Right, it's the complex conjugation. This is the fixed part under complex conjugation. And so you could just map it to the quotient, local quotient, and this actually turns out to be an isomorphism, which requires an argument but yeah. Okay, so you have all these things, and now they're nice and canonical. So in fact, this isomorphism I used, okay, so the upshot of this is psi C induces a canonical map. Canonical up to, I fixed Q bar and C at the very beginning. What is it? I call it upsilon. It also goes from the same group because I haven't changed anything on the left. I said C mod IC is S mod IS, and that's actually canonical because we remember, just to get from C and to think of it as inside T quo, I had to identify T sub with H, but mod I, that's canonical. So I evaluate at that canonical generator, I get something in T quo mod I T quo, which is canonically S mod IS. So I get a canonical map like this. And now you'll notice this is between exactly the same groups that my var pi was between, but in the opposite direction. And so this is of lambda tilde modules when I use a Galois action on the left and Hecke inverse diamond action on the right. So what's the conjecture? Well, actually, the form of the conjecture that appears in the paper is this. I suspected the stronger form, so I'm going to put the weak form. So here's the weak form of the conjecture. There exists a unit in, in lambda tilde. Yeah, really, it's the units in lambda tilde. Okay. Okay, such that the composite of the two maps, right, which are now an endomorphism of the group, is multiplication by this U in either direction. And this U is canonical. And what is U then? So the stronger form of the conjecture is that U is 1. These are inverse maps. Okay, so that seems rather strange, I would think, because remember, this var pi is like a totally explicit map, right? I defined it just completely explicitly. Well, this upsilon is somehow extracted from the proof of the main conjecture, right? And is not explicit. I mean, unless you consider this connecting, this sort of cocycle that comes from a Galois extension class to be explicit in some sense. Okay. So let me next say what's known about this. So let me define the derivative of the p-adic L function. Okay, so in the kth eigenspace, or the 2 minus kth eigenspace really, I can think of ck prime is just an element such that ck prime of my fixed generator to the s minus 1 is the derivative. There should be a constant, but I'm just going to ignore it because it doesn't make any difference for the theorem. The derivative of the p-adic L function for the omega to the k at, s minus 1. Right? It's exactly the derivative. Remember, xi, yeah, so I should say, just to recall, ck epsilon s minus 1 was lp omega to the k s minus 1 for all s and zp. And so we can just put those all together in a package in the appropriate eigenspaces of the plus part of lambda tilde. Remember, lambda tilde was zp of the gal f infinity over q. So that has Galois group zp cross. Okay. So great. So the theorem of Fukaya and Kato is as follows. The derivative of the p-adic L function times this composite, right? So this composite maps is an endomorphism of s mod is. I can multiply it by this derivative. Everything's mod xi, just remember, because these both have characteristic ideal xi, and neither has any p torsion by Ota's result. This is true. It's true after multiplication by xi, that the composition is 1, whatever that means. So some remarks. One is their result actually was on S, not on S mod is, but on S mod is tensor QP, which is somewhat different, but we improved this to get rid of the tensor QP. But also, this improvement in a totally different way also follows from Ota's result. Because the key difference is that what could happen when you tensor with QP, this could have p torsion, and then you wouldn't know what happens on p torsion. But Ota's, you see, x infinity minus has no p torsion, right? So if it's isomorphic to S mod is, then S mod is has no p torsion. So we're okay. The second one is if we had something, so Van der Rohe's conjecture or Greenberg's conjecture would imply that this x infinity 1 minus k for k even is not quite cyclic, but pseudo-cyclic, pseudo-isomorphic to a cyclic lambda module. And if we had this, this would imply, together with the above, the weak form of the conjecture in the omega to k eigenspace. 2 minus k eigenspace, actually. Eigenspace. There's some weird thing with k and 2 minus k. Right, well, you can see it, right? If I take the 1 minus k eigenspace here, then this thing has an omega to the 2 minus k action. Okay, and this would imply in particular the conjecture of McCallum and myself, and that's why it's known for p less than 163 million. The third is that if it happens that this p-adic L function has no multiple roots or no irreducible square factors, right, then strong form holds. And of course, it seems kind of unlikely that it ever does have any multiple zeros, but that seems very far from being proven. No. Okay, so also some related results. We can say that the big Hecke algebra, this was the Hecke algebra acting on modular forms, is Gorenstein if its lambda dual is isomorphic to it as a Hecke algebra. What's its lambda dual? Well, that was the lambdatic modular forms. So you can do this for big H or little h and S. Is free of rank 1, it is rank 1, over H, so isomorphic to H as an H module. So Wake and Wang-Erickson proved that if the 2 minus kth eigenspace, that's some even eigenspace, but not the one reflected from the 1 minus kth, is 0, then this H in the 2 minus kth eigenspace is Gorenstein. And in turn, that implies actually that S mod IS is the Eisenstein ideal mod at square. So that's kind of interesting. And also, if little hk is Gorenstein, so the cuspidal one, this is true if and only if, and this is just a consequence of Ota's result, this is cyclic. But I should say this is Ota, but this extends a result of Wake and Wang-Erickson. Okay. So, right. So let me just say out loud. Right, no, okay, I'll say why the derivative, right? Where is the derivative coming in? It's kind of surprising. Here, here, right, on both sides. So why C prime, I'll just say something very brief. On the left, it comes from cup product with the log of the cyclotomic character, in some sense. That somehow derivative of that. There's a way to interpret cup product with log of cyclotomic character as this derivative. On the right, it's coming from a p-adic regulator computation of these cup product, of these valence and Coteau elements. Okay, it appears there somehow. Okay, so now I just want to end with an alternate form of this conjecture to tie it in with the end of the talk last time. It's not one it used to be my favorite version of the conjecture. When I first formulated, I formulated 5 equivalent versions. But since then, I've always talked about the other one, so maybe it's good to mention this one. So alternate form. Okay, so essentially this Coleman map that appeared, or something close to it. Well, it's not really that. Okay, but this in John's talk, a map appeared from x infinity minus 1 to lambda tilde plus, if you like. And this thing has torsion kernel and finite co-kernel. You can make this canonical. So somehow this is going to come from the Galois action on cyclotomic units. You can construct this out of action of this group on cyclotomic units and get a map like this. So let me just say that the kernel is isomorphic to this. I take the opposite action on the Iwasawa adjoint, but don't worry about that. It's isomorphic to this Iwasawa adjoint of the plus part of x infinity. And the co-kernel is isomorphic to the Pontryagin dual of the maximal finite submodule of x of the plus part of x infinity. So if Van der Waals conjecture holds, both of these are 0, and then this is an isomorphism. Okay, so I could tensor product this thing with upsilon. So what does upsilon? Upsilon starts as a map on x infinity minus 1, and this thing starts as a map on x infinity minus 1. So I can make the 1's cancel. This is, right, the 1's cancel. And so, and what do these things go to? This first one goes to S mod IS, and the second one goes to lambda tilde plus. Okay, so we'll need that. The second thing is I had this S reciprocity map in the last talk. If I restrict it to cyclotomic units, then it always lands in x minus tensor x minus. So this was the S reciprocity map for the extension gal m infinity over for the maximal S ramified extension. Okay, for the S ramified Iwasawa modules of the maximal, the extension given by that over F infinity, the S ramified Iwasawa module, P ramified Iwasawa module. So there's some S reciprocity map here. I said I would take 3 extra minutes. So, right. So that's the first and the second ingredient, and the third ingredient is there's what I'll call a universal Maser-Tate element, L, inside S ord tensor, completed tensor product. Don't worry about that. With lambda tilde plus. This is actually has some explicit description, so let me just write it real quick. This is what interpolates the various p-adic L functions of ordinary cusp forms. I'm taking half of it, actually, only for the plus part here, but that's all we need. So we're on ordinary parts, so it makes sense to take up to the minus r. So I think of this as that, and then I put group element here, stick it here on the right at the rth level, and then I take the inverse limit. So I think of this as group ring over SR ord at finite level, group ring for Z mod P to the RZ cross, and then I project to the plus part. So this is some very explicit thing, but this is like the power series corresponding to an L function, right? And what L function? This gives you the Maser Kitagawa 2-variable p-adic L function. That's what I called it in the paper. But really it's a universal Maser-Tate element, because these things are called Maser-Tate elements. So, okay. So, great. So here's the equivalent form of the conjecture. If I apply, so here, so if I, 1 minus zeta will be my compatible sequence under norms of 1 minus p power roots of unity. I can apply my S reciprocity map to this thing that lies in C infinity. And then this group, right, x infinity minus tensor x infinity minus, the two different, I can apply upsilon tensor phi to it. And then the answer is I get this L, what I get is this L mod I. Or if you like, the image of L in S mod IS tensor lambda tilde plus. So what this is saying somehow is the conjecture is saying that the S reciprocity map interpolates lots of L values mod P, or mod the Eisenstein ideal is better. For cusp forms that are congruent to some Eisenstein series like EK of weight 1 and level weight K and level 1, any such cusp form, eigenform, is going to interpolate its L values. So let me just relate this to the structure of Iwasawa modules very quickly, because I had this theorem at the end of last time. if we took G to be x infinity minus, which was the Galois group of, well, okay, we'll just call M infinity the extension given by this Galois group. And suppose, just to make things life simple, that Van der Waals conjecture holds. Then there's the exact sequence of lambda tilde modules. Just write exact sequence. And the sequence is this. The second graded piece in the augmentation filtration of the completely split Iwasawa module, that was a quotient of the unramified thing, over M infinity, is almost isomorphic to this tensor product modulo psi applied to 1 minus zeta, the group generated by that. And the co-kernel is x infinity minus tensor 2. Yeah, so this is somehow a structure theorem for this potentially very, this piece in the augmentation filtration of the completely split Iwasawa module over a very large Kummer extension of F infinity. And somehow it's controlled by this thing, well, actually, what I should have said here is that this is the same as, right? What I should have said is that this is S mod IS tensor lambda tilde plus mod L bar, right? So it's being controlled by this thing which appears in the main conjecture, residual main conjecture for, it's the residual thing in the main conjecture for modular forms. So anyway, okay, so I think I'll end there.
Okay, is there any time for one short question? Questions?
Oh, yeah, thank you.
Okay, let's take a 25-minute break.